All right, let's continue with Chapter 1, talking about plate tectonics, continental drift, and seafloor spreading. There's probably way more information in this slideshow than you need, but the more the merrier in this case, so might as well learn it. So the theory of continental drift, like we said already in class, Alfred Wegener came up with this idea that the land on the Earth is in motion, and he did this in the early 1900s, and he was criticized for the scientific community. They thought he was crazy. Nobody believed his ideas because he really didn't have the evidence to support them. So, what was he thinking in terms of his evidence? Well, puzzle piece evidence, climate evidence, land and rock evidence, and fossil evidence. The idea that these things don't make sense unless the landscape around the world was actually in motion. So let's look at puzzle piece evidence. Continents fit together like pieces of a jigsaw puzzle. And we can easily see that with South America and Africa. But yes, spanning from that Pangea, that supercontinent, and then moving outward. Those pieces of land fit together like a jigsaw puzzle. Land and rock evidence. We have identical rock types as if they were matching from one mountain belt that was created at the same time on opposite sides of the Earth. And so we have some rocks in North America that are identical in every way, shape, and form to rocks in Europe. So they must have been created at the same event and then moved apart from each other over time. Fossil evidence. We have fossils of the exact same creatures spanning different continents, and these creatures could not have possibly swam across the oceans as they are today. Also, plants. Fossil evidence of the same plants on different continents, and we know they're not swimming, and so that gives rise to the idea that these organisms lived in areas that were once touching. And the last one, climate evidence. We are finding fossils of tropical plants in areas that are way too cold right now to have tropical plants growing there. And we are also finding coal in areas that are cold. And there's no way that there was plant life that would turn into coal in those cold areas. And so they must have moved around the globe. So those are the 4 pieces of evidence that Wegener came up with. But again, they weren't supported. He couldn't actually support those pieces of evidence. Just didn't have the technology at the time. And so let's fast forward 40-some years to the idea of seafloor spreading. So in the mid-1950s, several geologists started studying the seafloor using a technology called sonar. So they mapped the Atlantic Ocean, the bottom of the Atlantic Ocean, to read its topography. And in doing so, they found what we now call as the Mid-Atlantic Ridge, a giant ridge line that is running directly in the middle of the Atlantic Ocean, separating North and South America and Europe and Africa. And so this idea now came apart with this kind of mirrored image of this dividing line where new rock was being created on this point, and then the ocean floor was actually being pushed in both directions at the same rate. So the idea that the seafloor was actually spreading from a centered point, we call that a mid-ocean ridge. Evidence for this seafloor spreading actually occurring, well, there was active fractures in the lithosphere along the ocean floor in a pattern that exactly mimics the shapes of the coastlines. You can see that in this image. And so that means the idea that the continents on both sides were moving at the same pace from this center point, because it's a perfect mirror image of the edges, those borders of those land masses. Another piece of evidence was that the age of the rock got older the farther you got away from the mid-ocean ridge. And that would support the idea that if rock was being created at the mid-ocean ridge, then it's the newest rock, and as it gets pushed to the side, it's older and older and older and older. And then therefore the oldest rock would be located right next to the continental shelves, right next to the continents, but still oceanic crust. And that held true. The rock actually got older the farther you got away from the mid-ocean ridge. Another piece of evidence scientists came up with was the idea that, okay, if new rock is being formed at this ridge line, and we know that Earth systems, Earth processes, work to break down rock over time, wouldn't it make sense that there would be more broken down rock or sediment on top of the ocean floor the farther you got from the mid-ocean ridge? If the rock is older, there should be more sediment on top of it because there's been more time for sediment to break down, rock to break down into sediment and fall on the ocean floor. And that actually held true as well. Deposits of sediment along the bottom of the ocean continuously got thicker the farther we move away from a mid-ocean ridge. Another piece of evidence supporting the idea that the seafloor was spreading. And the last piece of evidence, I've talked about this one a bunch of times now, was the idea that the magnetic reversals captured in solid rock of iron filament in the rock. So these magnetic reversals show that the Earth's polarity has changed over time, and so iron is pointing north in some bands of rock, iron is pointing south in some bands of rock. But the key feature here is, if you look in the image on the left, the banding is patterned. So let's say if the polarity was south, rock equal distant both sides of the ridge line, the mid-ocean ridge, was pointing south. Therefore, that rock must have been created at the exact same time, so all of it, all the iron filament would point south, and then it got pushed in both directions, creating that mirrored banding of these rock intervals. So 4 pieces of evidence that supported the idea of seafloor spreading. The seafloor was actually widening from a given point, and the beauty about that is it then supported or made everything kind of make more sense. Subduction zone and trenches. If oceans are widening, why is the Earth not getting larger? Well, something's got to give, right? Give and take. So we're expanding one part, well, then we have to destroy another part, and this is where subduction zones come into play. Oceanic crust actually gets recycled back into the mantle at convergent plate boundaries, where an oceanic plate collides with a continental plate and then subducts and remelts back into the mantle. And this is a very clear image of seeing that process of the plate subduction and then remelting into the mantle. And then we'll talk about superheating magma and rising plumes to create disturbances on the Earth's surface as well. All right, continental drift, and then the supporting evidence of seafloor spreading. Now we get into the meat and potatoes that is pretty much the explanation for all geological processes, plate tectonics, and why the surface of the Earth looks like it does. So with the discovery of the features of the ocean floor and the mounting evidence that the seafloor was spreading in places, the idea behind the continental drift, Alfred Wegener's idea, reemerged as the theory of plate tectonics. Finally, this guy is going to get the credit he deserves because he was actually right. So the theory of plate tectonics is the idea that the lithosphere, the cold, hard, rigid, breakable crust of the Earth, is actually set up in a certain number of plates that are floating on the mantle. They're in constant motion, moving around the globe. And what is causing this? Well, convection currents. Convection drives plate motions. So the idea of the mantle, that semi-solid kind of plastic-like middle layer of the Earth, is being superheated from more interior layers of the Earth. And we know that heat rises, and as heat rises, it then cools and condenses and sinks back down. And so we get this cyclical motion of these convection currents in the mantle, and that is what's causing this churning to happen. And this is the driving force of plate motion. This is why plate tectonics happen. And much like in the atmosphere, heat rises and cools and condenses and sinks back down. And again, that is the cyclical motion. Convection currents are involved in the production of new rock on the Earth's surface. And you can see in this CGI image here how the convection currents bring up hot molten lava or magma, creating a divergent plate boundary, and then it's cooling and subducting back in. And I got a sweet video to show you kind of bringing it all together. So here we go with that.
It happens because hot rock rises, heated by the Earth's core. Near the surface, the rock spreads in two directions and goes sideways. It begins to lose heat. Eventually, the much cooler rock sinks back down. Through this spreading process, the Earth's crust is very slowly dragged apart. And it's this that ultimately causes the continents to move. Where the plates collide, the rock on the seafloor containing carbon from the dead plankton is carried deep into the Earth. As it descends, this layer of rock is heated, so the rock melts, releasing carbon dioxide. And gas is returned back into the atmosphere during an eruption. The remarkable cycle is complete.
So that was a little more full circle, and I think video images is way better than still images to give you an idea of how that process is happening. So let's dive a little bit deeper into plate tectonics. So again, we talked about the type of crust. There are two types, oceanic crust and continental crust. Both make up the lithosphere. Oceanic crust is more dense than continental crust. Therefore, it will always subduct under continental crust. Keep that in mind. It will always subduct. Continental crust does not subduct. It's too buoyant. It always stays floating on the asthenosphere. All right. You guys have all heard of Pangaea. It was the most recent supercontinent. 250 million years ago it existed and started breaking apart or splitting apart, and until we have what we see today. And let's fast forward 250 million years from now, we're probably going to end up with another supercontinent. Karaoke moment. Anybody interested in some extra credit and want to have some fun? Looking at you, Henry. Talk to me about your karaoke moment you can perform for the class. Okay, plate boundaries. Now the nitty gritty of plate tectonics. There are three types of plate boundaries. Divergent boundaries, we also call them spreading centers. Convergent plate boundaries, we also call them subduction zones. Transform boundaries, they're just transform faults. At divergent plate boundaries, the plates are moving apart from each other. What is caused, or what is created? Tensional stress, tension, pulling apart. What is formed? Mid-ocean ridges and rift valleys. So, kind of 3 bullet points there. Divergent plate boundaries, again, pull apart, create tension. New rock is formed, usually underwater at spreading centers, but sometimes we have continental rifting. We call that rift valleys. An example of this, a very famous example of this, is the Mid-Atlantic Ridge, the one that we mapped first to kind of solidify the idea of seafloor spreading and the theory of plate tectonics. Continental rifting, again, the crust is getting thinner, it's pulling apart, and it's broken and stretched. And so in areas of this, we typically have a lot of geothermal activity. Iceland has all kinds of geothermal energy plants and a lot of hot springs, things like that, because the crust is thinner in this continental rifting. And we believe it's happening in Southern California at the Salton Trough as well, someday going to connect Baja California and the Salton Sea. Another example on Earth would be the African Rift Valley. The continent is actually pulling apart, and so it's going to continue pulling apart and separating the continent. Convergent plate boundaries, my favorites, because they do the most stuff for us in terms of creating the landscape we see and enjoy on Earth. Convergent plate boundaries are when two plates collide into each other. They smash into each other. What kind of stress? We're talking about compression. Crushing a can, it's compression. And there are actually 3 different types of convergent plate boundaries. It can happen in one of 3 ways. The one we always talk about is continental oceanic conversion. Then there's oceanic convergence. And then there's continental convergence. So 3 ways in which the different plates can actually collide into each other. Again, what happens at convergent plate boundaries? Plates are being pushed together, compressional stress, rock is being destroyed, typically subducting into the lithosphere, and we get a whole series of things created from that. In this image, you can see a deep ocean trench forming and a continental volcanic arc, but we'll talk more about this in a second. And here we go. So the 4 things that are typically created at a convergent plate boundary: where the plates collide, we get a deep ocean trench. And then we get the creation of what's called an accretionary wedge. It's the scraping of the oceanic crust and piling onto the continental crust. And then we get a four-arc basin, an area of stuff not really happening. And then we get the most spectacular thing, a volcanic arc, where it's a line or a chain of volcanoes that create a mountain belt, right? Because that superheated rock floats back up through the crust and then erupts onto the surface of the earth, creating these chains of mountains, either on land, continental volcanic arcs, or underwater, volcanic island arcs. And the last plate boundary, or transform boundaries, formed when 2 plates are sliding past each other in opposite directions, horizontally, right? Horizontally past each other in opposite directions. This creates shear stress. We associate transform faults most with earthquakes. An example of one would be the San Andreas Fault, the big transform fault running north and south along California's close to the coastline. Again, review of transform boundaries. Plates are sliding past each other. Shear stress is being created, causes earthquakes to happen. And it also creates a lot of tears along mid-ocean ridges, so it displaces mid-ocean ridges side to side. And here's an example of that. You can see a mid-ocean ridge being displaced perpendicular to how the ocean ridge is actually happening. But in transform faults, plates are moving they're sliding in opposite directions past each other. All right. Let's talk a little more about those collisions one more time, because what's being created. So we have 3 types of potential plate collisions at a convergent plate boundary. The most typical would be an oceanic continental collision, where the denser oceanic plate always subducts under the continental plate. And this creates, again, these 4 things: ocean trenches, accretionary wedges, four-arc basins, and continental volcanic arcs. Why am I so hell-bent on talking about this specific plate collision? Because it is the story of California. If we look at California's profile, we have the deep Monterey Trench. We have the coastal range, which is the accretionary wedge. Again, not very big mountains that are not solid rock. They're just piled rubble. Then we have the four-arc basin, which is pretty much the Great Central Valley. And then we have the continental volcanic arc, which is the Sierra Nevada and Cascade Ranges. So this oceanic continental collision is the story of California. This is how California came to be. These 4 things are visible. We live on them. We experience them. This is exactly how California looks because of this oceanic continental plate collision in our history. Another type of plate collision is oceanic plate collision. In this case, one oceanic plate will subduct under the other one. It still will subduct under the other one. And those 4 things, again, are still created: a deep ocean trench, an accretionary wedge, a four-arc basin, and a volcanic arc. But in this case, volcanoes aren't being created on land. They're being created underwater, and therefore we get a line of volcanic islands instead of a line of volcanic mountains on land. So that's really the only difference, is the chain of mountains being created are islands instead of mountains on land. An example of this would be the Aleutian Islands in Alaska. You know, that big old finger that sticks out of the western side of Alaska, those are just a chain of volcanic islands created from a oceanic convergent plate boundary. All that this subduction zone created that volcanic island arc. And then the last and most magnificent one would be the continental plate collision, where two continental plates are actually colliding. So you can see in the image below that India, that used to be an island, that continental crust on the lithosphere, is heading towards Tibet continental crust. And continental crust is just too buoyant. It cannot subduct. So what is its only other option? To smash together like Play-Doh. And this is where we get folded mountains. So much pressure is being created that it's folding the rock, kind of like dough, into itself to create new rock types and to create massive, massive mountains. And that is why the Himalayas are the world's tallest mountains by far, more than twice the height of the Sierra Nevada, because they're not created by volcanoes. They're created by taking a continental crust, another continental crust, and just smashing it together and piling it on itself and folding it into massive, massive, massive mountains. All right. We're going to stop there. There's so much more to talk about in terms of mountain building and the different types of folds and faults in rock and how that leads to earthquakes, but we're going to save that for earthquakes. I want you now to pause the video, or stop the video, it's going to end, and go to back into Classroom and open up 1.3 Plate Tectonics review, and go ahead and take your time, do your best on answering those review questions that you just heard in the slideshow. You're more than welcome to reopen the video and cursor back and forth through it as you're answering these questions. Totally fine with me. For homework over the weekend, make sure you complete your slides for the California Naturalist Chapter 2. Next week, we'll keep doing peer presentations, and I will continue sharing a little bit more on Chapter 1, Earth Systems, out of the Barron's book. You guys have a great weekend. Please get outside and do something fun. And I will see you on Monday.